So good morning once again. I am Baris ÇIFTÇI. I'm the Director of Industry Analysis at the World Steel Association. I oversee the association's economic analysis work on the steel value chain, starting from energy and raw materials markets to steel-using sectors such as automotive and construction. Decarbonization is probably the biggest challenge humanity has ever faced. And by now we have a very good idea about the central role played by the energy systems in this challenge, the way we generate energy and the way we consume energy. For example, we can all drive electric vehicles, but charging those vehicles by power coming from a coal-fired power station defies the purpose, doesn't it? And similarly, now many steelmakers around the world have quite ambitious 5-year, 10-year, 25-year decarbonization plans and targets. And all of those plans and targets are contingent on the reliable supply of economic low-carbon energy, particularly low-carbon electricity. However, the central factor remains highly uncertain. That's why we've decided to devote this first session of our second Breakthrough Technology Conference to the role played by energy, the availability of reliable, economic, low-carbon energy, low-carbon electricity, the role played by this in decarbonization of our industry. I will start with a scene-setting presentation, aiming to provide an outlook on the evolution of energy demand and supply, particularly low-carbon energy demand and supply. Then I'll hand over to Dr. Thomas HANSMANN from the SMS group. He'll be talking about the steel industry decarbonization options in different settings with different energy characteristics. And then we'll have Professor SHEN Yansong from New South Wales University in Australia. Professor SHEN is leading the Green Metals Lab at this university, and he'll be presenting the work they are doing there, particularly the work that is focused on low-carbon iron technology development. So, Thomas, Professor SHEN, may I please invite you to join me on stage? Thank you. So let me start with our scene-setting presentation. Let me move on to the content slides of my presentation immediately. As you can see, I'd like to start with an overview of the current global energy landscape. Then I'll move on to the outlook part, where we will consider several projections so that we can build a reasonable outlook on the future of energy demand and supply globally. And I'll try to conclude with a summary of the main observations coming out of this brief analysis. Let's start with our overview of the current global energy landscape, starting from the supply side of the equation. In 2024, it was estimated that about 650 exajoules of primary energy was supplied. And the slide on this chart shows the fuel source breakdown for this supply. And you can see natural gas, oil, and supply represented about 80% of the primary energy supply. That is, in year 2024, the global energy system was by and large fossil fuels dependent, as it has been for the last century. And wind and solar, despite very rapid expansion during the last decade, represented less than 3% of global primary supply, energy supply in the year 2024. Moving on to the demand side of the equation, it was estimated that 650 exajoules of primary energy supply was used to meet a final demand of 450 exajoules only. That is a loss of about 200 exajoules during the conversion of energy or during the distribution and transmission of energy. About 1/3 loss of the primary energy supply, pointing to quite big inefficiencies in the current global energy system. And we'll come back to that because a major expectation and a major assumption in most projections is that the global energy system will become more and more efficient going forward. The pie chart on this slide shows the energy carrier breakdown for this final energy consumption of 450 exajoules. And now you can see electricity and heat there because some of the fuels were converted to these forms of energy and used in these forms. And you can see that electricity represented 21% of the total. That is, the global energy system had an electrification level of 21%. So this is where we are in our decarbonization journey. And the chart on the right-hand side shows that 14% of the global final energy demand was met by renewable sources. So 21% electrification level and 14% renewable energy level for our global final energy consumption. This is where we are in our decarbonization journey. Zooming in on the consumption, energy consumption can be grouped broadly into two big groups. As you can see on this pie chart, industry is the biggest one, accounting for 40% of the total, and that includes the use of fossil fuel as feedstock in industry. Then we have buildings and transportation, each accounting for about 30% of the total, and the rest, which is about 5%, is the energy demand coming from agricultural activities, fishing, and so on. Let's now zoom in on the energy mix for each of these big energy-using blocks. Transportation on the right-hand side, buildings in the middle, and industry on the left-hand side of this slide. Starting with transportation on the right-hand side, you can see that transportation was dependent on oil, that's this big orange part of the pie chart, at a level of 90%. And this is despite, again, the very rapid electrification of passenger vehicle sales. So we should be at around 20-25% of global sales nowadays. Transportation is still dependent on oil. Buildings in the middle, you can see the highest electrification level at 40% of the energy mix for buildings energy consumption, and the lowest fossil fuel dependence. If I can sum these up quickly, 23%, 10, 33, so 35% only fossil fuel dependence. That's the lowest among the three blocks. And industry, we see an electricity share of 23% and fossil fuel share of about 63%. So here I'd like to bring your attention to buildings, why we have this very high share of, or the highest share of electricity and lowest fossil fuel dependence. That reflects the ease of electrification of energy use cases in buildings. It's cooling, it's heating, cooking, so of course powering up appliances. So these are easy to electrify, and hence the high share of electrification of energy use in buildings. Let's now zoom in on the energy use of industry. You can see here the major industrial energy users, the so-called hard-to-abate sectors. Chemicals, iron and steel, and cement together account for 60%, about 60% of global industrial energy use. That is, hard-to-abate sectors are heavy industries which are really energy intensive, and their sheer volume, sheer output means that these are the biggest energy users. And in the rest, which represents about 40-45% of the global industrial energy use, we have mainly manufactured goods sectors, vehicles, appliances, textiles, foods, and all of these. Well, hard-to-abate sectors, why are they hard to abate? We all know very well. First of all, these sectors require very high heat applications, which are very difficult to electrify. Moreover, they use carbon-containing materials as feedstock. In contrast, manufactured goods sectors, they're using mostly low to medium heat processes, and they are much more easier to electrify. I'll conclude this part with going through the energy mix for these important energy users: iron and steel on the right-hand side, then cement and chemicals, the three hard-to-abate sectors, and manufactured goods, which are the easier part to decarbonize in industry. Looking at iron and steel, we see that we are consuming every year about 35 to 40 exajoules of energy, about 7-8% of the global total final energy demand. And 75% of that comes from coal, the big black block. Actually, the rest is mostly natural gas, electricity, but if you also take into account that the electricity we use, the direct heat we use also comes mainly from fossil fuel sources. Actually, direct and indirect, our industry is dependent maybe up to a level of 85%, 90% to fossil fuels at the moment. And when we turn to the energy mix for other sectors, we also see the very high coal dependence for cement and relatively high share of electricity for manufactured goods sectors. Let's now move on to the outlook for global energy demand and supply. By now, we are quite familiar with energy demand and supply projections. The most renowned one may be the IEA projections. But many of these projections start with a target, the Paris Agreement objective of keeping the global warming less than 1.5 degrees, or net zero at 2050, net zero at 2060. So they start with a target, and then they just assume the changes that need to happen to meet these targets happen at lightning speed, ignoring real-life constraints. So they show what must happen to meet a target, not what is likely to happen. And of course, for today's purposes, we cannot take those projections into account. Instead, we will make use of the projection set provided by the 9th release of the Energy Transition Outlook made by a company called DNV. This company is a Norwegian company operating in the assurance and risk management space, mainly in the energy area. And because developing a clear understanding of the future of energy is important to this company, they work out these projections, provide them every year. We believe that these projections come from an independent source. They do take into account the real-life constraints, plus all of their data and assumptions are available on public domain. So let's start with DNV's global primary energy supply projections, which you can see on the left-hand side of this slide. The first observation I'd like to underline is that from the current levels, global energy supply is expected to grow only 10%, despite the considerable expansion that is expected to be seen in global economy and population, only 10% growth, and then leveling off as from 2030s. And as I mentioned before, this inefficiency, the great or very high level of inefficiency of the current global energy system, well, it is expected to become more and more efficient, both on the demand and supply side. On the supply side, wind and solar are more efficient electricity generation technologies than combustion-based technologies. On the demand side, electric vehicles are more efficient than ICE vehicles, and so on and so forth. And the second observation, as global energy supply levels off as from 2030s, we see an accelerated green transition. You can see the dark blue part, which represents the total fossil fuel share, total fossil fuel supply, starting to come down steadily at an accelerating pace, and the corresponding void being filled by solar and wind at an, again, accelerating pace, and also nuclear. You can see, for example, wind and solar growing from 9 and 13 exajoules to 62 and 107 by 2050, and nuclear doubling from 29 to almost 60. So, according to these projections, actually, global green transition of the global energy system is expected to reach an impressive pace of, you can see the bottom line of the bottom row of the table, fossil fuels coming down by about 15% every decade starting from 2040. So this is an impressive pace. However, despite this impressive acceleration of the green transition, in the year 2050, according to these projections, the global energy systems will still be reliant on fossil fuels at a degree of 50%, pointing to continued scarcity of low-carbon energy on the supply side. So let's move on to the demand side and see what we can take away regarding the availability of low-carbon energy. Let's start with transportation. In transportation, we also see a little bit of growth in the total demand. We've mentioned the efficiency of electric vehicles. And despite very rapid ongoing electrification of the global road fleets, because the ICE vehicles we are buying nowadays and in the coming years will stay in use for a long time, actually the fleets will be electrified only to up to 50% by 2050, which means global transportation sector will remain reliant on oil up to a degree of 50% by 2050. You can see the very rapid growth in the electricity consumption of the global transportation sector up to 2050. But this chart tells us that transportation sector's electricity demand, particularly low carbon electricity demand, will continue to grow at an accelerating pace beyond 2050, at least for several decades. Buildings. Here we see steady growth in energy demand, reflecting the steady growth or the expectation for steady growth in global population becoming wealthier, so on and so forth. So compared to 2024, 2050 figure is 30% higher. And we've mentioned buildings have the highest share of electricity in their energy mix, about 40% nowadays. It is expected to grow only up to 50%. Again, the share of electricity, the amount of electricity used by buildings is expected to grow very strongly, but not only up to 2050, also beyond 2050 for several decades. So already the point I'm trying to make is that when we look at also to the consumption side, the message we are getting is low carbon energy availability, particularly low carbon electricity availability, might be expected to remain scarce for the foreseeable future. But let's move on and look at industry. The total demand for global energy coming from global industry sector expected to show a weak growth only, and that again reflects the assumptions for substantial efficiency gains, increasing use of recycled materials. That's okay. And when we look at the share of coal, the black part, we see that it starts coming down steadily, but slower than the pace we see for other sectors, transportation and buildings. And we see also the blue part, the share of electricity also growing steadily, but again at a somewhat slower pace when compared with the other two sectors. So all in all, we are seeing a slower decarbonization pace for industry, but this is not surprising, right? Looking in a bit more detail on the iron and steel sector, the two basic assumptions are that the global steel demand will grow by 10%, and will kind of reach a peak and level of around the peak level in early 2030s. And the share of electric furnaces in global steel production will grow up to 50% by 2050, as EAFs are more energy efficient than BF-BOFs. This will mean that globally, iron and steel making, although the demand will be higher, will require significantly less energy. So compared to 2024, the 2050 total energy consumption is like 8 exajoules. It's like 20% lower, if I'm not wrong. And when we look at the share of coal, we see it's coming down significantly from about 75% nowadays to around 45%, if I'm not wrong. Share of electricity growing, and interestingly, share of hydrogen reaching almost 15% by 2050. This is a strong assumption, as several speakers already pointed out the difficulties and the delays in plans. But something which is in line with these observations, we see hydrogen, this dark blue part on top, showing the scale-up stage only in 2040s, not in 2030s, which is in line with what we see on the ground with postponements of several hydrogen steelmaking projects. So all in all, a significant progress, this projection suggesting, but also quite far away from being comprehensive. we've pointed to the necessity for, or the expectation that decarbonization will follow different routes in different parts of the world, reflecting the differences in operating environment characteristics. I just want to say this is nothing new. If you can look at the chart on the left-hand side of the slide, showing the share of EAFs in different parts of the world, starting from the year 1980, you can see Japan, North America, China, EU, at about 25% level, at very close levels, back in 1980. And look at where they are now, how different the evolution of steelmaking technology has been in these different parts of the world. And if we focus on Japan, North America, and EU, they share one common characteristic. These are scrap surplus regions. They are net exporters of scrap, but in terms of energy availability and in terms of some other characteristics, they have big differences, we know. But already, when we look at the evolution of steel production technology from 1980 at major steel producing regions, we already see different approaches, and this is likely to be the case also under decarbonization pressures. One interesting observation coming from the DNV work, when we compare their projections across hard-to-abate sectors, iron and steel, petrochemicals and cement, steel is the one that is expected to show the fastest progress. You can see their projections for iron and steel on the left-hand side. You can see a significant decline, and here now we have 2060 as well, in the share of coal, the bottom part, or the share of fossil fuels. But you can see for petrochemicals and cement, there is only a marginal decline in their dependence on fossil fuels. This was an interesting observation. Manufactured goods, which are much more easier to electrify. Here we see the energy mix projections. First of all, we observe a significant growth in the overall demand, reflecting the expectation of global population growth, population becoming more affluent. But also we see the share of electricity increasing, but still reaching a level of around 50, maybe 55%. So again, similar to transportation and buildings, also manufactured goods sectors will continue to demand growing amounts of low carbon electricity, also for several decades beyond 2050. And lastly, emissions, the emissions corresponding to these projections. Well, a significant progress in decarbonization of the world economy with a decline of about 40% from the current levels. But that's not in line with the Paris Agreement objective, as we already know. This is more in line with a trajectory of 2.2 degrees warming by the end of the century. And the chart on the right-hand side again points to the difficulty of decarbonizing industry. The bottom two shades show the total emissions coming from industry. The gray shade shows the emissions coming from the rest of the global economy. So we see the emissions coming from other sectors come down much more rapidly when compared with manufacturing, despite the steady progress that is expected to be seen in the manufacturing sectors, decarbonization of them. So quickly summarizing the main findings coming from this analysis. First, decarbonization, the green transition of the world economy and global energy systems will accelerate as from 2030s. Second, despite this accelerated progress, despite the significant progress that the humanity is expected to show by 2050, this will be far away from being a comprehensive decarbonization. This will be significantly slower than the Paris Agreement objective. Low carbon energy availability, when we look at both the supply side and the demand side, we are seeing very strong signs that the world will remain a place where low carbon energy, particularly low carbon electricity, is scarce. By 2050, almost all end-use cases, and many of these will be easier to electrify when compared with hard-to-abate sectors, will be showing growing demand for low carbon energy, particularly low carbon electricity. And also interestingly, if it comes to the allocation of this energy, there is the possibility that these other sectors which are easier to decarbonize might be prioritized. Simply, they might have higher capability in terms of affordability, in terms of access to energy, but also in terms of the infrastructure requirements of the global energy system, in terms of the ability to connect the renewable energy sources to the demand centers and to manage the volatility of the renewable energy sources. So this concludes my presentation. Thank you so much for your attention. Without giving any break, we'll move on to Thomas. Thomas, may I give you the microphone? Thank you.
Thank you to World Steel Association for having us again this year in this conference. So it's a pleasure for us to come here and to debate with you about what we can do to fight global warming. Even if sitting here in this room, I was hoping a little bit of local warming wouldn't be so bad. It's cold inside here. So let's start with my talk, and we want to give you a little bit of insight about the way how we tackle the development that is taking place around this decarbonization topic. And we have heard already that luckily the number of technical solutions is steadily increasing. So we have seen that a new combination of known processes, new processes under development, which are all contributing without any doubt to the target to decarbonize steelmaking. But the variety of solutions is creating problems, because if I put myself now in the shoes of our customers, what are the right selections, what are the right decisions that have to be taken in order to assure production, steel production for the future, respecting the decarbonization goals, and of course respecting the economic targets, because we should not forget about that. We are living in a world where decarbonization is happening not in parallel, so there is different speeds and different markets, and the market is globally, so we have to compete. So what is the right choice? What can we do in order to maintain our competitiveness and to fulfill climate charges? And we want to avoid to come into such a conflict where we have to put against each other the climate ambitions and targets against economic ambitions. And what we have to look for are balanced solutions where we can fulfill both. So, stepping forward in the decarbonization of the steel industry without losing competitiveness. So that's simple, and it sounds simple, but unfortunately real life is complex. And I think you know this, and we have heard this already in several talks this morning. Unfortunately, the world is getting more complex if we step further and further into decarbonization, because there are other elements that are impacting our steel production. So energy is the topic of this session here. So of course, energy means electricity, it means natural gas. And if you look into what happened over the last years in the development of energy prices, which were beyond the experience of the past, so it makes everything a little bit more complicated to predict what is the right choice for our technology. H2 hydrogen, we have talked about a lot. When I started here in this conference, it was the first topic to be mentioned, the possibility and the trust that hydrogen can be the right solution to decarbonize industry, but we are looking desperately to find this hydrogen because the production is expensive, and we are lacking in time behind, and availability is not given. So hydrogen was the motor and accelerator for all the decisions that have been taken in the European steel industry to invest heavily into new facilities. All were aimed at using hydrogen. So, but nobody knows today when this will be available in quantity and price that will allow production of steel. The ore question is something that is of highest importance for all our assessments regarding economics, because also here big change is happening. We have the problem of high quality, low quality iron ore availability. We are living in a steel world where all the processes are optimized by high-grade ores, especially if we looked into direct reduction in the classical natural gas-based way. We are aiming at, or we need high-grade pellets. We know that there's a shortage, so there will be problems in the future. And open-end questions will be, what is the right feedstock for the future? CO2 certificates, there will be different regimes. We know it from Europe. The ETS mechanism will be extended to other places. CBAM, all these questions have a huge impact on the question to which are the costs and prices of steel in the future. Scrap, we know that the conversion from coal-based to electric steel making is the most easy way to decarbonize steel production. But if you talk to at least in Europe, to the classical mini-mill producers, they are all sweating because they know that the availability of scrap is going down the more electric arc furnace will be installed. This means there is a fight in view that to assure and to have access to the raw material scrap. You have the development that even integrated steel makers like ArcelorMittal, they are investing into the availability and the purchase of scrap. They are heavily investing into the improvement of quality of scrap. So this is a topic that is hot and will be determining for the future. And it is clear that we have heard that here several times. Integrated steelmaking will not disappear because we need this also for quality reasons. And this scrap topic, it goes along with the question of scrap substitutes. And scrap substitutes, the classical HBI, DRI, we know very well, but we believe that there will be more to come regarding pig iron, for instance. Pig iron that can be produced even in mines where low-grade ores can be converted into making use of smelter technology into a more green product that will be appreciated in the electric arc furnaces. So I think it's a topic that will become and will gain importance, and I think I share this view with Alexander Fleischander that in future there will be a decoupling of primary, secondary steel making, because it's obvious that you go to the place where energy is available at low cost, mostly green, and if you combine that with the mining process, then I think it makes a lot of sense. So all this makes life much more complicated for someone who has to decide what to do for the future, and this is then topped with the more soft topics like politics. We have seen what may happen. The green premium, which was in debate, where everybody is looking for, will this ever happen? The product requirements, so how can I change my production route if I want to continue to produce automotive exposed? So I think there's a lot of questions that have to be answered in order to make the right choices. This is not only a question for steel producers, it's also a question for us as a plant builder and solution developer, because the question is, where are we heading to? What is really missing, and where should we invest in order to find solutions that can fit into the needs of the future and find new solutions that can open options that today are not there. And in order to, as good engineers, in order to try to rationalize this discussion, we have, together with in our green steel team, developed an assessment tool that tries to give a more objective view on what is or might be the right way for the future, integrating the CO2 impact of the different technologies that we have, looking into comparisons of technologies, doing OPEX analysis. I think that's something that we wanted to analyze which technologies under which circumstances guarantee the lowest OPEX per ton of liquid steel for the steel producers, because automatically this is the most interesting one. And of course, last but not least, as we are a plant builder, so we have also something to say in this topic of CapEx. So, and I think that is the last puzzle piece that has to be fit in order to make a complete assessment. I just want to give you here as an example how this kind of analysis may look like. And I just want to mention that we are offering this as a service for you in order to do this jointly, collaboration with you, in order to see under these specific local conditions that are in India different than they are in Australia and different than they are in Europe, to find out what might be the right choice for the future. Here in this example, for different technologies, easy melt, some words about easy melt. What is easy melt? This is our answer to the question, how should look like the blast furnace of the future? And it's the easy melt name stands for something much higher philosophically and important. It means electrically assisted syngas smelter. So what we want to do is we want to convert the blast furnace into something different, where you no longer put blast, means hot air, in. This is why the name is changing. And this is one way to produce in the future liquid pig iron. Then, of course, you have the combinations of direct reduction with the classical way, with the electric arc furnace, or the new way, the smelter way, what we are building in Germany, in Thyssen. And the last topic, which is interesting, and I think that's something that might have potential for the future. This is fine ore reduction. CFB stands for circulating fluidized bed. So that might be the way, in combination with a smelter, to produce, for instance, green pig iron. So we looked into the different process routes, and not only by the rule of thumb of good engineers, but there is behind is process and energy balances and models. And if you look into the different production ways, you see that two topics that are important for the cost of this race. This is hydrogen and raw material. So it's in all the processing routes, it's the most and the dominating cost driver. It's above 50%. So there's much more, and if you look into this famous other topic that is mentioned there is natural gas, there is coke breeze, and there's coking coal costs, and a lot of other things in. So all this is in the model, but we wanted to, or I wanted to pick out the most important one if we look about hydrogen in combination for steel production for the future. So, and the question was, for these different processes, how does this impact? And let's look now into how it looks like. So what you see here, this graph, is the four technologies that I mentioned, and it shows the area where the operating costs are the lowest. So this is not absolute values, because these absolute values are nonsense, because it differs from every steel plant. Here it is based on European scenario. There is fixed cost there is 150 euro per ton of CO2 in. So all this is fixed, but the question is only if I vary only hydrogen cost and the pellet, so meaning the input of iron ore, into the process, how does this impact the choice of technology? Looking at the lowest production process that is available. And you see, in today's conditions, surprise, surprise, the most interesting way is the blast furnace. So it is still the most cost-attractive way to produce steel today. And if you now make a step and you move the cost for raw materials and hydrogen down, and the cost for high-grade ores up, then you see that all of a sudden other technologies are becoming much more interesting. So easy melt as our blast furnace derivative operating with hydrogen, or also the DRI OBF route becomes more interesting. So again, it is not a question now of tons euro per ton of steel that is important here. It only shows that the impact only of two parameters have a major result in the choice of the right technology. And if you make the next step and we change, because we are talking here about energy, we change the energy cost. Energy cost means in that case electricity. So the picture changes again. So if you lower the energy costs, more and more is the high electricity consuming process is interesting. And if cost goes up, you see that in that case, our easy melt technology becomes more interesting because it consumes less electrical energy than the other ways. So all this means you have to look carefully into the selection of technologies, and it is not so easy to anticipate how these cost-driving elements are developing in the future and what is the most flexible solution that you can think of in order to be sure that also in 5-10 years you are able to sell the steel that you are producing. So again, this is an example, and we have already exercised this with several steel producers in order to adapt this kind of scenario analysis for local conditions. And again, it depends. It is different in Japan than it is in Korea and than it is in India. So, and we are offering this as a service to help and to find a way. And it was also an analysis that we have done for ourselves in order to see where are technologies that are interesting for us to develop. And you can see here out of these graphs, of course, easy melt is one of the most important things. And also the combination of fine ore reduction, fluidized bed with a smelter is another one. And some words to these both technologies. Easy melt, Jochen Borg has already mentioned that this morning after signing an MOU with Tata Steel, I think one and a half year back, this joint project has now passed the board of Tata and it will be realized. So Tata Steel will give us the blast furnace E in Jamshedpur, and together we will convert that into the first modified blast furnace. It's a small one, I think 600 cubic meter blast furnace, but we want to realize technology, and we want to see really the impact on the operation of such a modified blast furnace, and to see how our concept of injection of synthetic gases is impacting not only CO2 emissions, but also the operation of the blast furnace. And this is an intermediate step to then, with the experience gained, to go into the next level of, let me say, more adult, big-size blast furnaces. That is still a different step to be done. Fluidized bed, I think that's for the reason that the fine ores that are available and not marketable is an interesting source for the production of iron. Fine ore reduction with hydrogen is a topic. In order to accelerate this path, we have decided to acquire the fluidized bed technology together with the pellet and sinter technology from Metso Autotech. And from 1st January on, this is fully owned by SMS. So this will accelerate our way into industrial realization of such plants. And we are in discussion now about realization of plants modules up to 1 million tons. So the combination of fluidized bed with the smelter technology that we are realizing, building in Germany, in Thyssen, where each of these, there are two smelters with 1.2 million tons of pig iron capacity each. And of course, if we talk about, or we accept, let me put it in this way, we accept that the integrated steelmaking will exist, may it be 30 or 50% in the future. We still need sinter plants, we still need pellet plants, and also we have to decarbonize this process step as much as possible, and we are looking into this together with the colleagues, new colleagues that are coming from Metso Outotec into SMS. Yeah, to summarize now, I think the world is getting more complex than it was before, and we try to approach that problem by doing classical analysis in order to give guidelines and help and assistance to make the right choices and selections. Of course, I mentioned that the CAPEX topic is one on top, so it's not only OPEX, but also CAPEX. And also here you can see that different process ways have huge differences in investment. And all these together may lead to wise decisions how to save steel production and to guarantee sustainable production for the future. At this point, I want to thank you for your attention, and I'm open for any kind of questions. Thank you very much.
Hello everyone, this is Yansong SHEN from University of New South Wales, and today I will talk about our research and on the Ironmaking decarbonization and our view and ideas about the Ironmaking decarbonization and how to achieve this. So right now I'm running a research lab called SHEN Lab of Computational Process Engineering for the green metals. And right, so very quick overview about our R&D on the growing iron. So basically right now we have around 40 PhD and postdoc fellows, and we have 2 senior advisors from the industry, like Professor John Matheson and Professor Sharif Jahanshani. And right now we receive a lot of funding from the industry and from Australian governments to make us to conduct many industry-related research and also some independent research. And we have been working together with the industry for many, many years. As you can see from here, like the first example, Baowu, since 2011, we have been working with them on 4 3-year projects, and working with BlueScope Steel since 2004, and ArcelorMittal just from last year, and then Rio Tinto since 2012, and BHP since 2016. Yes, as a university researcher, we publish a lot in this area on the Ironmaking and steelmaking, and we work together with Ironmaking industry partners in these publications. As you can see in this diagram, we have around 40 people, and around 15 people are working on the blast furnace, Ironmaking and Ironmaking decarbonization, and 5 people are working on the electro smelting furnace, and 4 people are working on basic oxygen furnace, and 5 people on EAF, and 5 people are working on the DRI for the ESF, and 5 people are working on the fluidization, the flat smelting, and other emerging Ironmaking technologies. We have several approaches to achieve these goals. The first one will be the modeling, and we are working in the university again, so we do not have a big pilot scale plants. We don't run the industry furnaces, so modeling will be the one of the most advanced and we use to understand, design, and optimize the blast furnace and other Ironmaking reactors, like from the CFD to DM to machine learning to the HMB. And also we run some high temperature experiments, and we also have some technology evaluation analysis like LCA-TA. Right, so this is a summary about our research. And today we may talk about the blast furnace. And the first one will be the blast furnace technology, blast furnace project we are running right now. We give the new name for this blast furnace technology. It's called RISB. It's short for the, as you can see in here, all right, the right-hand side, the burden distribution, like sustainable burdens, together with the renewable injections at the bottom. And so this is a short name RISB. This project is funded by the Australian Renewable Energy Agency, Australian government. It's a 5-year project. We hope to test the new burden materials. We hope to test the new injectant, like hydrogen, biochar, and then produce the anode fines. And the burden material, we hope to test like a bio-coke, bio-iron, and hydrogen produce agglomerate. So from my view, blast furnace will be there for tens of years, and also we still need to use a blast furnace to achieve the so-called decarbonization targets. Although we have many emerging technologies, but we may still need to rely on blast furnace to produce low-cost products. We have been talking about the decarbonization in the recent years, but my view is decarbonization is one side of the coin. We also need to look at another side of the coin, which is a low-cost operation. In the recent discussions and the reports, we usually ignore this part, and this may be too ideal but it's a bit far from the real world. So in this project, we work together with many industry partners: Rio Tinto, BlueScope, Baowu, ArcelorMittal, Sino Steel, CEA, and Shogun. And as you can see, we work together with many industry partners. And in this project, we generated one patent, which is another example. This is how to use hydrogen in the blast furnace. We are one of the first research group to study the hydrogen injection. So you can see after we inject hydrogen, the raceway shape and size will be crazy. So we need to be careful when we use a hydrogen injection. So in that case, HMB model is one method, but not enough. We should use a safety method. And HMB method can give us some ideas, like left-hand side, this is the operating window if we just use a hydrogen injection. But right-hand side is operating window if we use hydrogen together with coal. So they can see hydrogen together with coal will have a larger operating window. That means higher furnace stability. But coal got a dirty name. People do not want to use coal. So we have a pattern. It's a coal injection of the hydrogen together with biomass. So this way we can save around 30% 30% carbon dioxide. All right, let's see the two examples of the technologies. And then we talk about something more scientific, more academic. Let's talk about one of the methods we are most proud of, which is blast furnace modeling. The first part will be the raceway modeling. So in the raceway modeling, we start from 2008. Back to then, we start from the steady state at the pilot scale furnace, and we published quite a few papers representing this paper. This model is very robust. And then we evolve this model from the pilot scale to the blast furnace scale. And we use this model to study the new technologies and also some conventional technology optimization understanding. And later on, we evolve this model from first generation steady state to the second generation, which is an unsteady state. Then we can see the the raceway shape and size, and which is very important for the hydrogen injection operation. And then we use a safety DM method to capture the particle scale information. And the third generation, we use a machine learning to capture the raceway shape and size in just a few minutes. So basically, in summary, the first generation, we can study the coal and the biochar operation, but it can only be used for the steady state. And the second generation model, we can use that to study not just coal, it's also the hydrogen injection. Then we can study the impact of hydrogen injection, not just on the coal combustion, but also on the hydrogen raceway and size. And the third generation, we use the machine learning method to predict this raceway shape and size and also the co-combustion in just like several minutes, which is like 500 times faster than the CFD method. All right, so that's the first one. And the second one is also the summary of our blast furnace models. This one will be the whole blast furnace model. So when we look at the whole blast furnace, we are all expert in this blast furnace, so we understand blast furnace first is a transient state process. Second is a 3D reactor. And third is a layer structure operation. And also we need to capture the cohesive zone and all the infinite phenomena. All right, so these are the challenges we need to capture. All right, so back to 2015, we start from the first generation steady state blast furnace model, which is a 3D version. And then, but you can see I give a hollow star because after that we found this model was not so robust, so we didn't use that model for the subsequent studies. Instead, we rebuild this model using the not commercial code, using the in-house code. And then we consider the first breakthrough is the layer structure. The all on iron. This is the first model that can consider this one, and later on this treatment has been followed by many other researchers. And then you can see we use this model to study the normal operation, to study the novel operations. And this is a steady state blast furnace model. But we also further develop this model to the unsteady state blast furnace. Then we can see the time evolution of the internal states of the blast furnace. That's very important when we have to handle some unexpected operations. And then we evolve this model from 2D to 3D. And last one, we have some software package for this purpose. So to summarize, the first generation, the first generation blast furnace model is for the steady state internal state, and the second generation will be for the unsteady state, especially useful for the unstable operation. And the third generation is a fast prediction. All right, so I'm the last speaker presentation in the morning, so I will go fast. And pretty much this will be the last slides. And I hope to give a summary of the blast furnace models over the past 60 years, from 1960s, and cover the time-wide, steady state to unsteady state, to the dimensions from 0D, HMB, to 1D, 2D, to 3D. I will not go to details. So basically, 0D to steady state, you can see all these contributions, and 1D steady state, all these contributions, and the 2D steady state, who is working on this area, and the 3D steady state, who is working on these areas. And then for the transient state from 1D to 2D to 3D, who is working on this area. So this diagram, this chart, in the future help to use this chart as a reference. When you need to work with someone, when you need to find some useful model for your operation, for your optimization, then maybe you can find the suitable modeler for your project. All right, so that will be all for my presentation. Hopefully we can save some time and we can have a lunch early. All right, and that should be all for my presentation. Thank you.
Well, we planned to have a brief Q&A session after the presentations, but I think we have already taken some time from the lunch. Am I correct? Is that correct? So maybe 5 minutes only? Okay, so then I turn to the participants. Are there any questions for our speakers, Dr. HANSMANN and Professor SHEN? Please.
Thank you. Hello? Yes. Good afternoon. Yes, this is S. Dhara from Steel Authority of India Limited. Professor Shen, it was first of all, it's a wonderful presentation, and the whole journey of modeling in blast furnace is very much described there. My only question is, these models are most of the lab scale and model development scale. And for validation part of the models, have you relied on actual blast furnaces of any industrial scale, or have you tested these in your lab scale, smaller pilot scale furnaces?
Sure, well, happy to answer this question. Yes, our research aim is to work together and work for the industry. So our models are largely the industry scale furnaces, but for different blast furnaces from Asian countries to the European countries. And the second question, more for model validation. Before this year, we use the measurement around the blast furnace for model validation. For example, the top gas temperature, and then the stave temperature measurement, and some two-year drilling experiments to validate our models, which is very around the blast furnace, I would say. But this year we are lucky, we are working together with ArcelorMittal, and they have some measurement of the internal phenomena. And that work will be published early next year. And our model, that's a very interesting story. When we start to work with ArcelorMittal, they do not give us they just give us the boundary conditions, material conditions. They didn't give us the measurement. Okay, Yansong, you just run your simulation. And after that, let's compare. All right? If your comparison is good, then let's continue our collaboration. If not, maybe we just stop here. And then it's like kind of a blind test. And like 2 weeks early, we have the meeting, and they told us, okay, the comparison is very good. So to answer your question very short, model validation, we do the we apply our model to the small reactors for drop tube furnace for the kinetics validation. For the also apply our model to the blast furnace, and to in terms of the top gas temperature, and more importantly, we validate our model in terms of the internal state, like a temperature and a gas composition measurement. I hope I answered the question.
Thank you. Yes, this one.
Thank you. I'm particularly intrigued by the model that Dr. HANSMANN presented there. It was about how the technology choices are made based on the conditions that are very vital to make something possible. A technology, for example, it might be very good. It might work in a certain area or region, but might not be very viable depending on the energy prices and all that. And it ties very nicely to the actual energy systems that Baris presented there. Is this model available for use, or is it only for the clients or the customers of SMS Group?
It is namely for our customers. So in order to do this kind of exercise jointly and to find out what is the right, might be a good way to move forward. That's the purpose. It's not on sale. It's not.
The adjoining question to that, so you said that, yeah, it will depend on region to region, because that result might change there. So can you tell us that how significantly does it change between different major regions?
But there are several examples for differences that have a huge impact. So starting with the energy costs, so this look into the situation of the European theater, where you have extremely high natural gas prices, electricity prices, but not overall. You have islands of happiness, like in Northern Europe, where even you can think about production of hydrogen at competitive prices. So I think it depends very, very much on this kind of figures, and the variety is huge. The variety is huge. So if you look, I'm referring to this Stegra case, they have a business there, because even if they go the radical green way, starting from electrolyzers, electrowinning of electrolyzers of hydrogen, doing direct reduction until the flat products, it makes a lot of sense to do this, but only there. It would never make sense to do this in Germany or in other places in Europe. So there are many examples of this. Not looking into raw materials and so on and so on.
Thank you.
Perhaps one last quick question. Yeah, gentleman over there. Yeah, one question over there. Behind Rizwan.
Good afternoon. I am Indranil Mojumdar, CGM Sinter Plant, Durgapur Steel Plant, Steel Authority of India Limited. My question is to Mr. HANSMANN. Since BA route will be still there for quite some time for steel making, and for deciding that technology, that sinter and pellet route, it will be used as a necessary evil because it is a part of the technology. So my question is, what is the percentage of pellet and sinter are you considering for designing your that technology and blast furnace?
I think that is not so much impacted by the combination of the input material. So because it's the substitute of coke. So the problem is how much coke you can reduce the coke burden in the blast furnace, and up to or down to which lower level you can go by injection of energy, high energy electrification of the blast furnace. And I think this is not so much depending on the burden mixture that you put in. So it will, as I mentioned, I think the sinter plant, sinter technology, and also pellet technology aiming at blast furnace, they will continue to exist.
So there
and at the end, it's an optimization of costs that it has to be done locally.
So nowadays we are increasing the pellet percentage, that pellet, sinter, and iron ore lump we are using. That is the modern concept is that 50% pellet, 40% of sinter, and 10% of lump. So will this be, this technology will continue for some time, or will be going on increasing the pellet burden percentage?
The increase of pellets is increasing productivity, so there are blast furnaces existing that are operating at 100% pellet burden. So I think this is a matter of economic optimization and productivity of the blast furnace and of the nature of the iron ore and the pellet. So it's a very complex story, but I think there is no limitation for going in both directions.
Thank you.
Thank you. I think this is a good moment to conclude our session because we would like to delay the lunch any more than this. So, Dr. HANSMANN, Professor SHEN, thank you so much for your contributions. I think we have small gifts for you.